Right now, without your knowledge, without your permission, and without any possibility of resistance, you are being pulled through space at 600 kilometers per second, not away from something, toward something, something massive, something hidden, something so large that when astronomers first calculated its gravitational influence in 1987, they initially refused to believe the result. The numbers seemed wrong. The scale seemed impossible. No single structure in the known universe should have this kind of gravitational reach. And yet, when the data was checked and rechecked across hundreds of galaxies moving in formation across millions of light-years of space, the conclusion was undeniable. Something was out there, something enormous enough to redirect the motion of an entire supercluster of galaxies, including our own Milky Way, including every star within it, including the planet you are lying on right now, all of it accelerating, all of it falling, all of it moving toward a point in space that we cannot even directly observe. The pull is real, it is happening, and it has been happening for longer than the Earth has existed. They called it the Great Attractor. Not because the name was dramatic, because no other name was adequate. The term was coined in the 1980s by a group of 7 astronomers who spent years mapping the velocities of galaxies across the local universe and discovered something that should not have been there. The galaxies were not moving randomly. They were not drifting in all directions the way you would expect from an expanding universe. They were streaming. Every galaxy in a region spanning hundreds of millions of light-years was being pulled in the same direction, toward the same invisible point, with a gravitational urgency that implied the existence of something beyond anything in the standard model of cosmic structure. The pull was real, the speed was real, the destination was real, but the destination was hidden behind a wall of gas and dust so thick that optical telescopes could not penetrate it. Whatever was pulling us was invisible, and it was enormous, and it had been there, doing exactly this, since before the first star in the Milky Way was born. Here is what nobody wants to hear. The speed at which you are falling towards the Great Attractor is not merely impressive, it is a number that should fundamentally alter how you understand your position in the universe. 600 kilometers per second. That is the peculiar velocity of the Milky Way, the component of our motion that exists above and beyond the expansion of space itself. It is the speed at which we are actively falling, the speed at which the Great Attractor is winning the gravitational argument against everything around us. At 600 kilometers per second, you would cross the continental United States in a little less than 9 seconds. You would travel from Earth to the Moon in roughly 10 minutes. In 1 hour, you would cover more than 2 million kilometers, and you feel none of it. You are sitting still, you are lying down, and the universe is dragging you towards something so massive that astronomers still argue about what it actually is, even after 40 years of study. If you find yourself drawn to ideas like this, if the strange geometry of where we are in the cosmos gives you both dread and wonder at the same time, then I want to ask you to do something simple. Hit that subscribe button and give this video a like. This channel makes documentaries about the most extreme and unsettling truths in space science, the kind of ideas that feel like they should be classified, and your support is what allows me to keep making them. Every like, every subscription genuinely matters, and I appreciate every single one of you who has already joined. Now get yourself comfortable. Turn off anything that does not need to be on. Let the weight of the day dissolve for a few minutes. Because what we are about to explore together is not just a story about a gravitational anomaly. It is a story about your location in the universe, your speed through it, and how completely invisible both of those facts are to your body every single day. The Great Attractor sits in the direction of the constellation Centaurus, roughly 250 million light-years from Earth. To put that distance in terms your mind can process, 1 light-year is approximately 9.5 trillion kilometers. 250 million light-years is a number that has no natural human analogy. It is simply incomprehensible in the way that makes your thoughts slide off the edge. And yet, across that incomprehensible distance, the gravitational influence of whatever sits at that location is strong enough to pull an entire supercluster of galaxies at 600 kilometers per second. Gravity weakens with distance according to the inverse square law. Double the distance and the gravitational force drops to 1/4. For something this far away to move something this large, this fast, requires a mass concentration that staggers the imagination. The total mass implicated in the Great Attractor region is estimated at several times 10 to the power of 16 solar masses. 10 to the 16th, that is a 10 followed by 16 zeros, each zero representing 10 times more mass than the one before it. The story of the Great Attractor begins in a windowless office in 1986, where an astronomer named Sandra Faber was sitting with a problem that refused to go away. Faber, working at the University of California at Santa Cruz, was one of the most respected observational astronomers of her generation. She had spent years developing techniques for measuring the distances to galaxies using the relationship between a galaxy's intrinsic luminosity and the spread of stellar velocities within it. In 1986, this method was one of the best tools available for mapping the large-scale structure of the nearby universe. Faber had assembled a collaboration of 6 other astronomers to apply this technique across hundreds of galaxies spread across the sky. The team had a nickname. They called themselves the 7 Samurai. What they found when they finished their measurements would shake the foundations of what astronomers thought they understood about cosmic structure, and it would reveal a gravitational force operating on a scale that no existing model of the universe had anticipated or predicted. The 7 Samurai, formerly comprising Donald Lynn Den Bell, Roger Davies, Alan Dressler, Sandra Faber, David Bohr Stein, Roberto Terlevich, and Gary Wegner, had set out to measure what cosmologists call peculiar velocities. In an expanding universe, every galaxy is moving away from every other galaxy as space itself stretches. But this recession is not perfectly smooth. On top of the general expansion, galaxies have additional motions caused by the gravitational pull of nearby mass concentrations. These additional motions are the peculiar velocities. Measuring them reveals where the mass is concentrated in the universe even when you cannot see it directly. What the 7 Samurai found was shocking. The galaxies were not just moving with the expansion of the universe. They were all streaming together in the same direction, with velocities that implied the existence of a mass concentration of unimaginable scale. In their landmark 1987 paper, published in the astrophysical journal Supplement, they named the source of this streaming motion the Great Attractor, and they estimated its mass at something approaching 10 to the power of 16 solar masses. Alan Dressler, who coined the term Great Attractor, was accustomed to surprising results. He had worked on galaxy clusters, on the distribution of dark matter, on the large-scale structure of the cosmos. But the scale implied by the streaming motion was unlike anything in his previous work. The galaxies in the survey were separated by tens of millions of light-years. They were members of different galaxy groups and clusters. They had no reason to be moving in coordinated fashion unless something genuinely massive was pulling them. Dressler later recalled that the team initially worried they had made a systematic error in their distance measurements. If the distances were wrong, the peculiar velocities would be wrong, and the Great Attractor would dissolve into a data artifact. They spent months checking every step. They ran the analysis multiple times with different subsets of galaxies. Every time the streaming motion came back, every time the implied mass was the same, There was no systematic error. The Great Attractor was real, and it was larger than anything any of them had imagined at the start of the survey. The fundamental problem with the Great Attractor, the reason it remained hidden for so long, has nothing to do with distance and everything to do with location. The Great Attractor lies almost exactly in the plane of the Milky Way, and the galactic plane is the single most difficult region of the sky to observe in optical light. Between us and the Great Attractor lies what astronomers call the Zone of Avoidance, a broad band of sky where the dust and gas concentrated in the disk of our galaxy absorbs and scatters optical photons so thoroughly that objects behind it are completely invisible. Thousands of galaxies lie hidden in the Zone of Avoidance. For decades, astronomers knew something was pulling them from behind this curtain, but they could not see what it was. It was like being able to feel the heat of a fire through a thick wall, but having no way to open a door and look directly at the flames. The Great Attractor exerted its pull through the dust as easily as if the dust were not there. Gravity does not require a clear line of sight. The Zone of Avoidance was not merely an observational inconvenience, it was a fundamental barrier that shaped everything astronomers knew and did not know about the nearby universe. In optical wavelengths, roughly 20% of the entire sky is obscured by the galactic plane. Within that obscured region lie some of the most massive concentrations of matter in the entire local universe. For years, cosmological models of the universe's structure had a blind spot built directly into them, a missing 20% that happened to include the region most responsible for the motion of our galaxy. The Great Attractor sat almost precisely at the centre of this blind spot. Astronomers calculated its properties from the effects it produced, the way a physician might diagnose a condition by examining the distortions it creates in surrounding tissue before ever being able to see the source of those distortions directly. The diagnosis was startling. The thing behind the wall was not a cluster. It was not a supercluster. It was something larger than the vocabulary of cosmology had yet developed words to describe. Breaking through the Zone of Avoidance required a different kind of light. Infrared radiation passes through dust more readily than visible light. X-rays penetrate further still. Radio waves are almost entirely unimpeded by galactic dust. Through the 1990s and into the 2000s, teams of astronomers turned instruments operating in these wavelengths toward the Zone of Avoidance and began for the first time to map what was actually there. What they found was a richly structured landscape of galaxy clusters and filaments, a cosmic web hidden behind the galactic curtain, and at its heart, centered roughly in the region where the Seven Samurai had predicted the Great Attractor should be, a massive concentration of galaxies called the Norma Cluster, formerly catalogued as AY Bell 3627. The Norma Cluster is one of the most massive galaxy clusters in the nearby universe. Its core contains thousands of galaxies packed into a region only a few million light-years across, and the total mass of the cluster runs into the quadrillions of solar masses, making it heavier than anything else in its immediate cosmic neighbourhood. The Norma Cluster was a revelation. Here finally was something visible, something measurable, something that could be weighed and mapped and placed on the three-dimensional chart of the local universe. Its mass was enormous by any standard, far more than any ordinary galaxy cluster. But here was the problem that immediately presented itself when astronomers did the arithmetic. The Norma Cluster was not nearly massive enough. When the gravitational calculations were run, when the measured streaming velocities of hundreds of galaxies across the entire Great Attractor region were fed into the equations, the answer came back wrong. The Norma Cluster could account for perhaps 30% of the pull, maybe 40% on the most generous assumptions. The remaining 60% the majority of the gravitational force moving an entire supercluster of galaxies through space at 600 kilometers per second was unaccounted for. The thing behind the wall was more massive than the thing they had finally managed to see. The wall went deeper than anyone had expected, and the mystery of what lay beyond it demanded a larger answer than any single cluster could provide. This discovery forced a realization that permanently changed the way astronomers thought about the large-scale structure of the cosmos. The Great Attractor was not a single object, it was not even a single cluster. The Norma Cluster was merely the densest visible node within a far larger region of enhanced matter density that extended across hundreds of millions of light years. The true Great Attractor was something diffuse and enormous, a broad region of space where matter had accumulated above the cosmic average through billions of years of gravitational attraction, pulling in galaxies and galaxy groups and clusters from all directions. Mapping this extended structure required tracking the motions of thousands of galaxies across the entire nearby universe. It required new techniques, new data, new instruments, and a new conceptual framework for thinking about cosmic structure on the very largest scales. That new framework arrived in 2014, published in the journal Nature, in a paper that fundamentally redrew the map of where we live in the universe and gave the Great Attractor the context it had always deserved. In September 2014, a team led by astronomer R. Brent Tully of the University of Hawaii, working with A.Y. Len Kor Tidwe of the University of Lyon, Yehuda Hoffman of the Hebrew University of Jerusalem, and Daniel Pomar Red of the Paris-Saclay University, published a paper in Nature that introduced a new concept to astronomy. They called it Laniakea. The name comes from the Hawaiian words for immeasurable heaven, chosen in part to honour the Polynesian navigators who crossed vast stretches of ocean guided by their deep understanding of the sky. Laniakea is a supercluster of galaxies, the largest coherent structure within which our Milky Way can be said to reside. It contains more than 100,000 galaxies spread across 520 million light-years. Its total mass is estimated at 10 to the power of 17 solar masses, roughly 100 million billion times the mass of our Sun, and at the centre of Laniakea, at the gravitational heart of the supercluster, sits the Great Attractor, the invisible engine that has been setting the direction of our cosmic journey for the entire history of our galaxy. Laniakea redefined what it means to have a home address in the universe. Before 2014, astronomers classified our location in a hierarchy of structures. Earth orbits the Sun moves within the Milky Way belongs to the local group of galaxies, the local group is a minor member of the Virgo supercluster. That was the standard description. The Tully team's analysis replaced it. The Virgo supercluster is not a distinct supercluster at all. It is merely an outlying tendril of Laniakea, a small branch on the vast filamentary tree of the structure that dwarfs it by orders of magnitude. Our address changed overnight. We are not in the Virgo supercluster. We are in Laniakea. We orbit its gravitational centre, the Great Attractor, in the way that Earth orbits the Sun, except the orbit takes far longer than any timescale relevant to human civilization, and the attractor is so far away, and the expansion of the universe so relentless, that we will never under any circumstances reach it. To understand the speed at which we fall toward the Great Attractor, you need to understand what 600 kilometers per second actually means in practical terms. Begin with the most familiar speed reference available. The speed of sound in air is approximately 340 meters per second, or about 1,200 kilometers per hour. A commercial airliner cruises at roughly 900 kilometers per hour. The fastest aircraft ever built, the SR-71 Blackbird, reached a maximum speed of about 3,500 kilometers per hour, or roughly 1 kilometer per second. Our peculiar velocity toward the Great Attractor is 600 kilometers per second. That is 600 times faster than the SR-71 Blackbird. It is 35,000 times faster than a commercial airliner. It is faster than most of the fastest objects humans have ever measured, with the notable exception of light itself, which travels at approximately 300,000 kilometers per second. We move at 1/500th of the speed of light silently, invisibly, every moment of every day. Translating the 600 km per second velocity into distances you can visualize reveals a truth that is simultaneously awe-inspiring and deeply unsettling. At this speed, in a single second, you travel 600 kilometers, approximately the straight line distance from New York City to Detroit. In 1 minute, you cover 36,000 kilometers, nearly the entire circumference of the Earth. In 1 hour, you cover 2,160,000 kilometers, more than 5 times the distance from Earth to the Moon. In 1 day, 51,840,000 kilometers, roughly 1/3 of the distance from Earth to the Sun. In 1 year, you cover approximately 18.9 billion kilometers, equivalent to roughly 2.5 times the distance from the Sun to Neptune. All of this is your personal cosmic velocity happening silently, invisibly, without disturbing a single object on the surface of the Earth, without altering a single weather pattern, without making any instrument you can hold in your hand register any motion at all. The universe is in constant motion, and the evidence is completely hidden from every sense you possess. The reason you feel none of this velocity is one of the most profound lessons physics has to teach. Motion by itself is not detectable. Only changes in motion are. This is the content of Galileo's principle of relativity, formalized 3 centuries later by Einstein into the special theory of relativity. If you're on a train moving at constant speed on perfectly smooth tracks, you cannot tell, without looking out the window, whether you are moving or stationary. The physics inside the train is identical whether the train moves at 0 kilometers per hour or 300 kilometers per hour. The same principle applies to the Milky Way. Our galaxy is not accelerating significantly toward the Great Attractor at this moment. It is moving at a roughly constant velocity, having been pulled gradually to this speed over billions of years by a steady gravitational force. Because the acceleration is so gradual, and because there is no friction in space, no resistance against which the motion can be felt, the journey is entirely invisible to every sense you possess. You will live and die in motion without ever feeling it. The calculation of our peculiar velocity toward the Great Attractor requires subtracting 2 very large numbers from each other. This sounds simple in description. In practice, it is one of the most difficult measurements in observational astronomy. The universe is expanding. Every galaxy is receding from every other galaxy as space itself grows. The rate at which a galaxy recedes from us depends on its distance, in a way described by the Hubble constant, a number that relates recession velocity to distance. For every megaparsec of distance, approximately 3.3 million light-years, galaxies recede at roughly 70 kilometers per second. This expansion velocity must be subtracted from the total observed velocity of a galaxy to isolate its peculiar motion, the part caused by gravity rather than expansion. But the Hubble constant is not perfectly known. The distances to individual galaxies carry substantial uncertainties. Every measurement of peculiar velocity is a difference between 2 large numbers, and differences between large uncertain numbers carry the largest possible uncertainties. The achievement of the 7 Samurai was extracting a real signal from an ocean of this kind of noise. The Seven Samurai worked around this measurement problem by using statistical methods across hundreds of galaxies. Any individual galaxy's distance measurement might be off, but if hundreds of galaxies all show coherent streaming in the same direction, the statistical power of that coherence becomes overwhelming. Individual errors average out. The systematic signal, if real, persists, and the signal they found was real and enormous. The streaming velocities they measured were not subtle. They were not borderline statistical artifacts. Galaxies across a region spanning hundreds of millions of light years, galaxies that had no business moving in coordinated fashion unless something genuinely massive was pulling them, were all streaming toward the same point at velocities between 400 and 700 kilometers per second, with the Milky Way itself moving at approximately 600. The coherence of this streaming motion across such an enormous region of space was, at the time of publication, the strongest evidence ever obtained for the existence of a super large-scale mass concentration in the universe. The Great Attractor was not inferred from the motion of one galaxy. It was inferred from the motion of hundreds of them, all agreeing. The measurement of our peculiar velocity is not just an astronomical curiosity, it has direct cosmological consequences. The universe on the very largest scales should be roughly homogeneous. Matter should be spread with approximate uniformity across the cosmos, with fluctuations present but not dominant. If there are regions where matter is far more concentrated than average, those regions generate peculiar velocities in nearby galaxies, velocities that deviate from the smooth Hubble expansion. The existence of the Great Attractor and the size of the peculiar velocities it generates tells us something fundamental about how matter is distributed on scales of hundreds of millions of light years. It tells us that the universe, at least in our neighborhood, is significantly less smooth than the simplest cosmological models predicted. The Great Attractor is a constraint on cosmology. It is evidence about the amplitude of matter fluctuations at large scales. It is a data point that theorists building models of cosmic structure must account for if their models are to be credible, and it remains one of the most important observational anchors for understanding the formation of large-scale structure in the universe. When the Norma Cluster was identified as the visible core of the Great Attractor region, astronomers began building detailed maps of the surrounding structure. What emerged over the following decades was a picture of breathtaking complexity. The Great Attractor region is not a simple spherical blob of matter. It is a three-dimensional knot in the cosmic web, a dense intersection of filaments, sheets, and voids that extends in all directions. Galaxy clusters are strung along filaments like beads on a wire. Between the filaments are enormous voids, regions nearly empty of galaxies, hundreds of millions of light-years across, where matter has been drawn away by the surrounding density concentrations over billions of years. The Great Attractor sits at one of the densest nodes of this web within our cosmic neighborhood, a place where multiple filaments converge and matter accumulates to concentrations that can redirect the motion of entire superclusters. It is the gravitational capital of our region of the cosmos, a meeting point of the largest structures the universe has built in our neighborhood. The cosmic web that surrounds the Great Attractor is itself part of a larger structure that reveals the true complexity of the universe. The web was first clearly predicted by computer simulations in the 1980s. Theorists working with gravitational dynamics simulations showed that small initial fluctuations in the density of matter in the early universe would grow over time through gravitational instability. Regions slightly denser than average would attract surrounding matter, growing denser still. Regions slightly less dense would lose material, becoming voids. The result, after billions of years of gravitational evolution, is a web of interconnected filaments and sheets surrounding enormous empty voids. The structures observed in galaxy surveys match this theoretical prediction with remarkable fidelity. The Great Attractor is not an anomaly in this picture. It is the natural outcome of gravitational instability acting over cosmic time. It is what happens when slightly denser regions of the early universe have 13.8 billion years to grow, to pull in their neighbours, to accumulate mass, and to become the dominant gravitational features of their region of the cosmos. The Shapley concentration changes everything. In the 1930s, American astronomer Harlow Shapley identified an unusually rich concentration of galaxy clusters in the direction of the constellation Centaurus, located beyond the Great Attractor at a distance of roughly 650 million light-years. For decades, the Shapley concentration was considered a significant but not central structure. That assessment was wrong. Subsequent surveys revealed that the Shapley concentration is one of the most massive concentrations of matter in the entire observable universe, an enormous supercluster containing approximately 10,000 individual galaxies. Its total mass exceeds 10 to the power of 16 solar masses. And here is the crucial point that many popular accounts of the Great Attractor miss entirely. The Shapley concentration is pulling us too. It sits in roughly the same direction as the Great Attractor, further away, and its gravitational influence adds to the pull already being exerted by the Great Attractor region. The combined effect is larger than either structure alone. We are not being pulled by one thing. We are being pulled by two enormous things stacked in the same direction, each one adding to the speed of our infall through the cosmos. Disentangling the contributions of the Great Attractor and the Shapley concentration to our peculiar velocity took decades of careful observation. The challenge is that both structures lie in the same general direction as seen from Earth. The gravity of each adds to our peculiar velocity, and separating which fraction of our speed is caused by which structure requires measuring not just the motion of the Milky Way, but the motions of thousands of other galaxies at different distances, all within the same broad region of sky. By the early 2000s, detailed surveys using infrared observations capable of penetrating the zone of avoidance had produced a clearer picture. Current best estimates assign roughly half of our peculiar velocity to the Great Attractor region and a substantial fraction to the more distant Shapley concentration. The exact contributions remain a subject of active research. A comprehensive survey published in the monthly notices of the Royal Astronomical Society in 2017 by Leavenworth and Hudson suggested that the Shapley concentration may be responsible for nearly as much of our motion as the Great Attractor itself. The total effect of both structures together makes our peculiar velocity far larger than either one alone could explain. There is a third player in this gravitational drama that is often overlooked: void repulsion. Between the Milky Way and the Great Attractor lies the local void, a vast region of space nearly empty of galaxies spanning hundreds of millions of light-years. Voids do not merely sit passively in the cosmic web. Because matter has been drained from them by the surrounding density concentrations, they represent regions of genuinely below-average matter density. And because gravity pulls toward mass concentrations, being near a void means being effectively pushed away from the void by the absence of gravitational attraction in that direction. The local void repels the Milky Way in the direction away from itself, which happens to be roughly toward the Great Attractor. This repulsion adds to the attractive pull of the Great Attractor and the Shapley concentration. Our peculiar velocity is therefore the result of at least three separate contributions: the gravitational pull of the Great Attractor region, the more distant pull of the Shapley concentration, and the repulsion of the local void pushing us away from empty space and toward the densest regions of the nearby cosmos. The concept of void repulsion was not widely incorporated into models of cosmic flow until relatively recently. For decades, cosmologists focused primarily on the attractive side of gravitational dynamics, mapping the mass concentrations that pull galaxies toward them. The role of voids in generating peculiar velocities through their absence of mass was recognized in principle but underestimated in practice. A landmark study published in Nature Astronomy in 2017 by Yehuda Hoffman and collaborators used a reconstruction technique applied to the CosmicFlows survey data to produce the most detailed map yet of the cosmic velocity field in our neighbourhood. Their analysis revealed that the local void is not just present, but actively important. The repulsion it exerts on the Milky Way contributes meaningfully to our total peculiar velocity. We are not merely being pulled toward the Great Attractor, we are simultaneously being pushed away from the enormous empty space behind us. The motion is driven from both ends, with the Great Attractor pulling from ahead and the local void pushing from behind, both forces acting in concert to produce the 600 km per second infall that defines our trajectory through the cosmos. Measuring the precise mass of the Great Attractor remains one of the hardest problems in observational cosmology. The difficulty is fundamental and comes from three separate sources. First, much of the Great Attractor region lies behind the Zone of Avoidance, where even infrared surveys provide only partial coverage. Second, the Great Attractor region is not a single collapsed object but an extended distribution of matter, spanning hundreds of millions of light-years, making its total mass inherently harder to define than the mass of a single galaxy cluster. Third, and most subtly, the Great Attractor region is not fully collapsed. It is still in the process of falling toward its own centre of mass, which means that the galaxies within it have their own internal peculiar velocities on top of the net streaming motion toward the attractor. Untangling these multiple layers of motion to arrive at a clean mass estimate requires extraordinary data and computational power. The current best estimates span nearly a factor of 10, from the most conservative to the most generous calculations. The Great Attractor is massive. Exactly how massive remains one of the open questions of modern cosmology. The CosmicFlows project, led by R. Brent Tully and his collaborators at the University of Hawaii and partner institutions, has been the most sustained and productive effort to map the velocity field of our cosmic neighbourhood. The project has gone through multiple data releases over the past 2 decades. CosmicFlows 1 contained distance measurements to roughly 1,000 galaxies. CosmicFlows 2 expanded this to approximately 8,000 galaxies. CosmicFlows 3, published in 2016, included more than 18,000 galaxy distances. CosmicFlows 4, published in 2022, contained nearly 60,000 galaxy distances, the largest homogeneous catalogue of peculiar velocities ever assembled at the time of its release. Each successive data release has refined the picture of the cosmic flow field, sharpened the definition of structures like Laniakea and the Great Attractor, and provided increasingly detailed maps of where mass is concentrated in the nearby universe. The result of this decades-long effort is a 3-dimensional map of gravitational influence that shows, with unprecedented clarity, the structure of the cosmos in which we are embedded and the direction in which we are being carried. The density of matter in the Great Attractor region, expressed as a ratio to the average cosmic density, is known as the overdensity parameter. In the core of the Norma Cluster, the overdensity is several hundred times the cosmic average. In the broader Great Attractor region as a whole, the overdensity is more moderate, perhaps 2 to 5 times the cosmic average, but spread across an enormous volume. The mathematical consequence of this distributed overdensity is profound. Gravity is cumulative. Every small excess of mass distributed across hundreds of millions of cubic light-years contributes to the net gravitational pull on surrounding galaxies. Individually, each contribution is small. Collectively spread across the vast volume of the Great Attractor region, they add up to a net force capable of moving entire galaxy superclusters at hundreds of kilometers per second. This is the deep lesson of the Great Attractor. You do not need a single catastrophically dense object to generate catastrophic gravitational effects. You need enough volume, you need enough distributed mass, and you need enough time for that distributed mass to make its presence felt across the enormous distances of the cosmos. The relationship between the Great Attractor and dark matter is a crucial chapter of this story that is rarely told in full. Dark matter, the invisible component of the universe that interacts only through gravity, accounts for approximately 27% of the total energy content of the universe, compared to roughly 5% for ordinary visible matter. In galaxy clusters and filaments, dark matter is the dominant component of the gravitational mass. For the Great Attractor region, this means that the mass you can see, the galaxies, the hot gas detected in X-rays, the dust and stars and clouds of material that show up in observations, accounts for only a small fraction of the total gravitational mass producing the streaming velocities the Seven Samurai measured in 1987. The Great Attractor is, fundamentally, a dark matter structure. It is an enormous overdensity of invisible mass that has accumulated along a node of the cosmic web over billions of years, with visible galaxies tracing its presence the way foam traces the surface of a wave, marking the deep structure beneath without containing most of it. The temperature of the gas in the core of the Norma Cluster gives us a direct measurement of the depth of the gravitational potential well at the heart of the Great Attractor region. In galaxy clusters, hot gas is trapped by gravity in a state called hydrostatic equilibrium. The temperature of this gas reflects how deeply it has fallen into the gravitational potential well. Deeper wells have hotter gas because the gas has fallen further and converted more gravitational potential energy into kinetic energy and then into heat. X-ray observations of the Norma Cluster, made by the European Space Agency's XMM Newton telescope, measured the temperature of the intra-cluster gas at approximately 8 kilo-electron-volt, or roughly 90 million degrees Celsius. For reference, the core of the Sun reaches approximately 15 million degrees Celsius. The Norma Cluster's intracluster gas is 6 times hotter than the center of our star. This temperature implies a gravitational potential well of immense depth, consistent with a cluster total mass of several times 10 to the power of 15 solar masses, and it provides an independent confirmation of the mass estimates derived from the peculiar velocity surveys. Radio observations have added another layer to the portrait of the Great Attractor region. Surveys in the late 1990s and early 2000s revealed that the Norma Cluster contains several major galaxy groups that are in the process of merging, falling toward the cluster's core along the filaments of the cosmic web. Galaxy cluster mergers are among the most energetic events in the universe. When two clusters merge, the collision of their hot intracluster gas generates shockwaves visible in X-rays. The kinetic energy involved in a major cluster merger is comparable to 10 to the power of 64 joules, a number that exceeds the total energy output of the Sun over its entire 10 billion year lifetime by many orders of magnitude. The Norma Cluster is not static. It is actively growing, actively accumulating mass, drawing galaxy groups toward it along the filamentary arms of the cosmic web and incorporating them into its ever-growing gravitational domain. The Great Attractor is not finished. It is still building. The process that began in the early universe continues today and will continue for billions of years into the future, adding mass to the densest node in our cosmic neighborhood. Beyond the Norma Cluster, the larger Great Attractor region extends into a vast network of clusters and superclusters that are all, to varying degrees, falling toward each other. The Hydra Centaurus Supercluster, of which the Norma Cluster is a part, is itself one of the major mass concentrations in the region. Further along the direction of the streaming motion lies the Centaurus Cluster, one of the closest rich galaxy clusters to the Milky Way, located about 155 million light-years away. The Laniakea Cluster and the Perseus-Pisces Supercluster in the opposite direction, and the Norma Cluster further out, are all embedded in the same large-scale gravitational landscape. They are all participating to different degrees in the flow field shaped by the Great Attractor and the Shapley concentration beyond it. The local universe is not a static place. It is a landscape of ongoing gravitational dynamics, of matter in constant motion, of structures forming, merging and growing on timescales that are incomprehensible by human standards but proceeding with absolute, unwavering inevitability toward a future state determined entirely by the physics of gravity and dark energy. The expansion of the universe provides a counterforce to the Great Attractor's pull that fundamentally limits where this story can go. Space itself is expanding, and that expansion is accelerating due to dark energy, the mysterious repulsive component of the universe whose nature remains one of the deepest unsolved problems in physics. Dark energy, which accounts for approximately 68% of the total energy content of the universe, generates a repulsive effect that acts against gravity on the very largest scales. For structures within a few hundred million light-years, gravity wins. The Great Attractor can hold Laniakea together, or at least slow its dispersal. But for structures separated by more than a few hundred million light-years, dark energy wins. The expansion of the universe tears them apart regardless of their gravitational attraction for each other. This competition between gravity and dark energy sets a fundamental limit on the size of gravitationally coherent structures in the universe, and ultimately determines the fate of everything the Great Attractor has been accumulating for billions of years. The outcome of this competition was written into the laws of physics at the beginning of the universe. The fate of the Milky Way in the context of the Great Attractor is more nuanced than a simple story of eternal infall. Yes, we are moving toward the Great Attractor at 600 kilometers per second, but we are not accelerating toward it at any pace that changes the overall picture. The peculiar velocity is roughly constant because the increasing distance between us and the attractor as the universe expands partially offsets the gravitational dynamics. Meanwhile, the acceleration of the universe's expansion due to dark energy is gradually increasing the rate at which space itself is stretching between the Milky Way and the Great Attractor. Over sufficiently long timescales, dark energy will win. The expansion rate will exceed our peculiar velocity, and the Great Attractor will begin to recede from us despite our continued gravitational attraction to it. We will fall toward it forever. We will get no closer. And eventually the space between us and the Great Attractor will be expanding so rapidly that not even light from the attractor's galaxies will be able to reach us, and our gravitational home will vanish beyond the cosmic horizon, invisible and permanently unreachable. This is the most disturbing implication of the Great Attractor story, and it is the one that most popular accounts fail to reach. The thing pulling us at 600 kilometers per second, the gravitational center of the supercluster we call home, is unreachable. Not because of the distance alone, though the distance is incomprehensible. Not because of the travel time alone, though that too is beyond anything that matters to a civilization of any realistic longevity. But because the universe is actively working against our arrival. Even if we could somehow build a spacecraft capable of 600 kilometers per second, the Great Attractor would still recede from us, because we would still be subject to the expansion of the universe, which stretches the space between us and the attractor at a rate that grows over time. There is no spacecraft fast enough. There is no technology conceivable within known physics that solves this problem. The Great Attractor is our gravitational home, and we can never go there. The universe built us a home and then made it permanently inaccessible by the laws it also built. The Hubble constant, the number that describes the expansion rate of the universe, is both the most important and the most contested measurement in modern cosmology. Its value determines how fast space expands per unit distance. Multiply the Hubble constant by the distance to the Great Attractor, and you get the rate at which space between us and the attractor is expanding. At a distance of 250 million light-years and a Hubble constant of approximately 70 kilometers per second per megaparsec, the recession velocity due to universal expansion is approximately 5,300 kilometers per second. Compare this to our peculiar velocity of 600 kilometers per second in the opposite direction, toward the attractor. The expansion is already winning by a factor of nearly 9 to 1. Our peculiar velocity is not carrying us toward the Great Attractor. It is merely slowing our recession from it. And as the universe continues to expand, the recession velocity will grow while our peculiar velocity remains roughly constant, widening the gap between our trajectory and any path that could bring us home to the gravitational center of our supercluster. The Hubble tension, a persistent discrepancy between different methods of measuring the Hubble constant, adds another layer of uncertainty to this picture. When the Hubble constant is measured from the cosmic microwave background, the relic radiation left over from the early universe, it comes out to approximately 67.4 kilometers per second per megaparsec. When it is measured from the local universe, using distances to individual galaxies calibrated through Cepheid variable stars and supernovae, it comes out to approximately 73 kilometers per second per megaparsec. This discrepancy of about 8 to 10% has persisted for years, despite increasingly precise measurements. It is statistically significant enough that astronomers have begun wondering whether it points to something genuinely missing in the standard cosmological model. Some have proposed new forms of dark energy, additional relativistic particles in the early universe, or modifications to general relativity. None of these proposals has been confirmed. The tension remains open, and it matters for the Great Attractor story because the exact expansion rate determines exactly how fast the universe is winning its race against the pull of gravity on the largest scales. The cosmic microwave background provides an independent and exceptionally precise measurement of our motion through the universe, and what it reveals is more than just our velocity toward the Great Attractor. The cosmic microwave background is the thermal radiation emitted when the universe first became transparent to light, approximately 380,000 years after the Big Bang. It fills the entire sky at a nearly uniform temperature of 2.725 degrees Kelvin, but it is not perfectly uniform. One of the largest features in its temperature distribution is a dipole pattern, a slight asymmetry in which one half of the sky appears slightly warmer and the other half appears slightly cooler. This dipole is caused by our motion through space. The side of the sky we are moving toward receives a Doppler blue shift, which raises the apparent temperature slightly. The side we are moving away from receives a red shift, which lowers it slightly. The amplitude of this dipole gives us our total velocity through the universe relative to the rest frame of the cosmic microwave background, and it is this measurement that provides the most direct evidence for the enormous speed of our cosmic motion. Our total velocity through the universe, measured against the rest frame of the cosmic microwave background, is approximately 630 kilometers per second. This motion is directed toward a point in the sky in the general direction of the Hydra Centaurus supercluster, consistent with the Great Attractor direction. But this total velocity is not simply our peculiar velocity toward the Great Attractor. It also includes the contribution of the Sun's orbit around the center of the Milky Way, which adds roughly 220 kilometers per second, and the motion of the Milky Way within the local group of galaxies, and the motion of the local group as a whole within Laniakea. What the cosmic microwave background dipole measures is the sum of all of these motions stacked on top of each other. Disentangling them to arrive at the net peculiar velocity of the Milky Way relative to the cosmic web requires subtracting each contribution in turn, a procedure that has been carried out with increasing precision over the past 3 decades using a combination of measured velocities, stellar kinematics, and detailed models of the local mass distribution. The Planck satellite operated by the European Space Agency between 2009 and 2013 made the most precise measurement of the cosmic microwave background dipole to date. The Planck results confirmed our total velocity through the cosmic microwave background rest frame at 627 kilometers per second, directed toward the Hydra Centaurus region of the sky. The precision of this measurement is extraordinary, determined to within a few kilometers per second, but precision in measuring the total velocity does not automatically translate to precision in measuring the contributions of individual structures. The Milky Way is moving toward the Great Attractor, yes, but we are also moving because of the Shapley concentration and the local void and the Virgo cluster, and dozens of other structures each contributing their own fraction of our total peculiar velocity. Disentangling all of these contributions is a problem that the most sophisticated peculiar velocity surveys with tens of thousands of galaxy measurements have only partially solved. The full accounting of every structure's contribution to our cosmic speed remains an active and productive research problem. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, located approximately 53 million light-years away in the direction of the constellation Virgo, also contributes to our peculiar velocity. The mass of the Virgo cluster is estimated at approximately 1.2 times 10 to the power of 15 solar masses, making it significantly less massive than the Great Attractor region but much closer. Its proximity means its gravitational influence is disproportionately large relative to its mass. The Milky Way's peculiar velocity includes a component directed toward the Virgo cluster that adds to or subtracts from the component directed toward the Great Attractor, depending on the geometry of each galaxy's direction in the sky. The net peculiar velocity of the Milky Way is the vector sum of contributions from Virgo, the Great Attractor, the Shapley concentration, the local void, and several less important nearby mass concentrations. The result points us generally toward the Great Attractor region, but the vector is not perfectly aligned with any single structure. We are pulled from multiple directions at once, and the Great Attractor wins the tug-of-war. The question of whether Laniakea is a real, gravitationally bound structure, or merely a dynamical convenience has been debated since the 2014 paper. Tully and collaborators defined Laniakea as the region of space where matter flows toward the Great Attractor rather than away from it, the basin of attraction in the language of dynamical systems. Within this basin, all matter participates in the net infall toward the Great Attractor. Outside it, matter flows away. This is a physically meaningful definition, but it comes with an important caveat. Gravitational basins of attraction are not the same as gravitationally bound systems. Water in a river basin all flows toward the sea, but that does not mean every drop of water will remain in that river system forever. Similarly, galaxies within Laniakea are flowing toward the Great Attractor, but whether they are actually gravitationally bound, meaning whether they will remain within Laniakea and ultimately approach the Great Attractor region, depends on whether the gravitational attraction of the supercluster can overcome the accelerating expansion of the universe over billions of years. The answer for most of Laniakea is that the expansion wins. A detailed analysis estimated that only the densest innermost regions of Laniakea are genuinely gravitationally bound. The outlying tendrils, including much of what was once called the Virgo Supercluster, will eventually be pulled apart by the accelerating expansion of the universe. The Milky Way itself, sitting in the outer regions of Laniakea, is likely not gravitationally bound to the supercluster's core. We will not fall into the Great Attractor. We will not merge with it. Instead, over trillions of years, dark energy will stretch the space between us and the Great Attractor faster than we can fall toward it, and the Great Attractor will recede from our view and eventually disappear entirely behind the cosmic event horizon, the boundary beyond which the accelerating expansion of the universe makes it impossible for any signal, any light, any information to ever reach us again. Our gravitational home will become unreachable, not gradually but absolutely, vanishing behind a horizon that no physics can cross. The cosmic event horizon is one of the most existentially significant concepts in modern cosmology, and the Great Attractor's relationship to it is deeply unsettling. The event horizon is not a physical boundary. It is a mathematical surface in space, beyond which the recession velocity due to dark energy exceeds the speed of light. Nothing can travel faster than light through space, but space itself is not bound by this rule. Space can expand at any rate, and if it expands fast enough, objects on the far side of the horizon become permanently inaccessible and eventually invisible. The light from objects beyond the horizon can never reach us because the space between them and us expands faster than the light can travel across it. The current cosmic event horizon is estimated to be roughly 16 billion light-years away. The Great Attractor, at 250 million light-years, is well within this horizon. We can see it. We can measure it. But the horizon is not static. As dark energy continues its work, more and more of the observable universe will slip behind the horizon and be lost to us, and our cosmic address will become progressively more isolated. The precise direction of the Great Attractor in the sky is right ascension approximately 10 hours and 24 minutes, declination -31 degrees and 31 minutes in the constellation Centaurus. This places it on the boundary of the Zone of Avoidance, partially behind the galactic dust but now accessible with infrared and radio instruments. In the southern hemisphere, on a dark night, Centaurus is one of the most spectacular constellations in the sky. Alpha Centauri, the nearest star system to our Sun, lies in Centaurus, as does the brilliant star Hadar. Somewhere beyond the rich star fields of the Milky Way that flow through this region of sky, beyond the dust and gas of our galaxy's disk, beyond the hundreds of millions of light-years of space between us and the gravitational heart of Laniakea, the Great Attractor continues its silent, invisible, unstoppable work, pulling the contents of a supercluster toward itself at a pace too slow for any human lifetime to detect but too relentless for physics to deny. It has been there for billions of years. It will be there for billions more, and we will keep falling toward it without ever arriving. The scale of the Great Attractor, in the context of other cosmic structures, helps to calibrate the magnitude of what we are discussing. Our Milky Way galaxy is approximately 100,000 light-years in diameter. The local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and about 50 smaller companions, spans roughly 3 million light-years. The Virgo cluster at its core contains approximately 1,300 galaxies in a region about 5 million light-years across. Laniakea, the supercluster centered on the Great Attractor, is 520 million light-years in diameter. The Great Attractor region itself, not just the Norma Cluster core but the entire extended mass distribution, spans hundreds of millions of light-years. Each structure in this hierarchy is larger than the last by factors of many. The Milky Way, which contains 400 billion stars, is a rounding error in the scale of Laniakea, and Laniakea is merely one supercluster in an observable universe that likely contains millions of similar structures, each with its own gravitational center, each pulling its own galaxies toward a destination they will never reach. The observable universe contains an estimated 2 trillion galaxies, a number revised dramatically upward in 2016 from the previous estimate of 200 billion, based on an analysis published in the Astrophysical Journal by Christopher Con Seh Lee and collaborators at the University of Nottingham. Most of these galaxies are too far away for us to observe in any detail with current instruments. Many are beyond our cosmic event horizon, and within the 2 trillion galaxies we can observe, those galaxies are organized into a hierarchy of structures, groups and clusters and filaments and superclusters, each embedded within the next. The Great Attractor is one node within this hierarchy, a significant node, the dominant gravitational influence in our cosmic neighborhood, the center of our supercluster. But in the context of the full observable universe, it is simply one of millions of similar nodes in the cosmic web, each pulling on its surroundings with the same relentless gravitational insistence, each the center of a basin of attraction containing hundreds of thousands of galaxies, each the great attractor of its own region of space. The discovery of the Great Attractor forced a revision in the concept of what it means to live in a typical part of the universe. For decades after the Big Bang cosmology was established, the universe was conceptualized as roughly homogeneous on large scales. Matter was spread across the cosmos in a pattern that, averaged over large enough volumes, looked the same everywhere. This principle, called the cosmological principle, is the foundation of modern cosmology. The Great Attractor did not refute the cosmological principle, but it demonstrated that the approach to homogeneity is far rougher and lumpier than the simplest models suggested. On scales of hundreds of millions of light years, the universe has enormous variations in matter density. The Great Attractor region is several times denser than the cosmic average. The adjacent voids are correspondingly emptier. The lumpiness is real, it is large, and it generates the enormous peculiar velocities that the Seven Samurai measured in 1987 and that cosmologists have been studying ever since. We do not live in a featureless cosmos. We live in one with geography, with texture, with structure that shapes where we are and where we are going. The history of the universe's large-scale structure begins in the first fractions of a second after the Big Bang, in a period of extraordinary violence and density when the entire observable universe was compressed into a region smaller than an atomic nucleus. During this period, quantum fluctuations, random variations in the density of the primordial energy field, were inflated to macroscopic scales by a process called cosmic inflation. These inflation-stretched quantum fluctuations became the seeds of all structure in the universe. Regions that were infinitesimally denser than average began to attract more matter through gravity. Over hundreds of millions of years, these slightly dense regions collapsed to form the first stars and galaxies. Over billions of years, those galaxies merged and clustered into groups, then into clusters, then into superclusters. Over 13.8 billion years of gravitational evolution, the infinitesimal quantum seeds of the Big Bang became the enormous structures we observe today, including the Great Attractor, which is ultimately an amplified imprint of conditions that existed when the universe was a tiny fraction of a second old. The connection between the quantum fluctuations of the Big Bang and the Great Attractor gives the structure a philosophical weight that purely astronomical descriptions cannot quite capture. The Great Attractor is not merely a gravitational anomaly, it is the legacy of quantum events at the birth of the universe. the random probabilistic variations in energy density that existed when everything was compressed into an almost unimaginably hot and dense state. Eventually, through billions of years of gravitational amplification, became the structure that now pulls you through space at 600 kilometers per second. There is a direct chain of physical causation connecting the quantum foam of the first instance of existence to the motion of the Milky Way today. The universe wrote its future into its first moments. The Great Attractor was always going to be there. It was always going to pull in this direction. The exact location, the exact mass, the exact speed of your motion toward it. All of this was determined before any star had ever formed, written into the laws of physics and the geometry of the early universe. The role of the Great Attractor in the formation and history of the Milky Way is a question that cosmologists have only recently begun to address systematically. For most of the Milky Way's history, the galaxy has been embedded in the gravitational field of the Great Attractor region and Laniakea, falling toward their center of mass. This infall has influenced the large-scale trajectory of the Milky Way through space, and through that trajectory, the environment the galaxy has encountered. The density of matter in the cosmic web varies dramatically from filaments to voids. The trajectory of the Milky Way through this web has determined which environments we have passed through, which neighbours we have interacted with, and ultimately which cosmic address we inhabit today. If the Great Attractor were located in a different direction or had a different mass, the Milky Way might be on a completely different trajectory, embedded in a completely different cosmic neighbourhood, experiencing a completely different evolutionary history. The Great Attractor shaped the Milky Way's path through the universe. It shaped the conditions under which our solar system formed. In a real and traceable sense, it shaped us. The gravitational influence of the Great Attractor also affects the pattern of the cosmic microwave background radiation in subtle but measurable ways. The integrated Sachs-Wolf effect, predicted theoretically in 1967 by physicists Rainer Sachs and Arthur Wolf, describes how photons gain or lose energy as they climb in and out of gravitational potential wells in the accelerating universe. When cosmic microwave background photons pass through a large overdensity like the Great Attractor region, they are slightly blue-shifted as they fall in, and then slightly red-shifted as they climb out. In a universe without dark energy, these two effects would cancel exactly. But in a universe with dark energy, the gravitational potential weakens slightly while the photon is inside it, because the accelerating expansion dilutes the matter density. The result is a net blue shift, a subtle hotspot in the cosmic microwave background map in the direction of large mass concentrations. This effect has been detected in the cosmic microwave background data in the direction of large superclusters, providing an independent confirmation that these structures are real, and that dark energy is real, and that both are doing exactly what physics predicts. Gravitational lensing provides yet another window into the Great Attractor's mass. When light from distant objects passes near a massive structure, the gravitational field of that structure bends the light, distorting the apparent shapes and positions of the objects behind it. For enormous structures like the Great Attractor region, the lensing effect is weak and spread over a vast area of sky, a phenomenon called weak gravitational lensing. Measuring this weak lensing signal requires averaging over hundreds of thousands of galaxy shapes to detect the coherent pattern of slight distortions caused by the foreground mass. This technique, applied to modern deep photometric surveys, has been used to map the projected mass distribution of the Great Attractor region independently of galaxy velocities, providing a check on the mass estimates derived from peculiar velocity surveys. The results are broadly consistent. The Great Attractor region is genuinely enormously massive, a conclusion reached by two entirely different observational techniques using entirely different physical effects, neither of which requires the other to be valid. The evidence is triangulated. The mass is real. The question of what the Great Attractor will look like in the future, on timescales of billions of years, requires tracing the dynamical evolution of the cosmic web. Computer simulations based on the lambda cold dark matter cosmological model have been run to predict the future state of the local universe at timescales of 10, 50 and 100 billion years. These simulations show that on timescales of a few billion years, the Great Attractor region continues to grow, accumulating mass from the surrounding filaments. The Norma Cluster and its associated galaxy groups merge into ever more massive structures. The richness of the cluster increases, the temperature of the intra-cluster gas rises, the X-ray luminosity increases, the dark matter halo becomes more concentrated. This growth continues until dark energy becomes dominant enough to cut off the infall of matter from progressively larger distances, leaving the cluster isolated in an expanding void, growing no further, ultimately the frozen core of what was once the gravitational capital of a supercluster, sitting alone in a universe that has expanded away from it in all directions. The discovery of the Great Attractor and the subsequent development of the Laniakea concept have had an impact that extends beyond astronomy into the broader culture of how humans understand their place in the cosmos. Before these discoveries, the hierarchy of cosmic structures was already humbling. Earth is small, the solar system is vast, the Milky Way is incomprehensibly large, but the Great Attractor and Laniakea are added new levels to this hierarchy that most people have not yet fully processed. We are not just in the Milky Way, we are in the local group, we are in Laniakea. We are in a supercluster 520 million light-years across, containing 100,000 galaxies falling toward a gravitational center we will never reach. Every additional level in this hierarchy compounds the sense of scale and the challenge of conceptualization. The Great Attractor is not merely a distant astronomical object. It is the address above our address. The city whose name we write below our own city on an envelope whose recipient lives in a world too large for the human imagination to hold without enormous effort. The measurement of peculiar velocities has advanced from a niche observational technique to one of the most powerful tools in cosmology. Modern surveys like the 6DF Galaxy Velocity Survey, the SDSS Peculiar Velocity Catalogue, and the CosmicFlows database have produced increasingly precise maps of the cosmic flow field. These maps show not just the motion toward the Great Attractor, but the complex three-dimensional velocity field of the entire local universe, a landscape of attraction and repulsion shaped by every mass concentration and void within several 100 million light-years. Reading this velocity field is like reading a map of invisible mass. Wherever matter accumulates, the velocity field converges. Wherever voids exist, the velocity field diverges. The Great Attractor shows up in these maps as the dominant convergence in our cosmic neighborhood, a gravitational drain toward which all the surrounding rivers of galaxies flow. It is the most prominent feature in the cosmic flow map of our region of the universe, and every new dataset that comes in confirms and refines its position, its mass, and the speed at which it draws everything nearby toward its center. The ROO Bin Observatory, now under construction in Chile at Cerro Pachón, will transform our understanding of large-scale cosmic flows when it begins full operations. The observatory is designed to image the entire accessible southern sky every 3 days for 10 years, producing a dataset of unprecedented depth and breadth. Among its scientific objectives is the measurement of peculiar velocities for millions of galaxies, several orders of magnitude more than current surveys. With this data, the velocity field of the local universe will be mapped with a resolution and precision that makes the current best maps look like rough sketches. The Great Attractor and its surrounding structure will be defined with exquisite detail. New structures, currently hidden beneath the noise of smaller datasets, will become visible. The history of our cosmic motion, how we got to our current velocity and trajectory, will be traced in greater detail than ever before. The ROO Bin Observatory will give cosmology new eyes to see the gravitational landscape in which we are embedded, and the Great Attractor will be one of its most studied features. The Square Kilometre Array, the largest radio telescope ever built, currently under construction with components in South Africa and Australia, will add its own revolutionary contribution to this story. Radio surveys can penetrate the zone of avoidance in a way that optical surveys cannot. The Square Kilometre Array will be sensitive enough to detect radio emission from hundreds of millions of galaxies at distances spanning much of the observable universe. Applied to the Great Attractor region, it will allow detailed mapping of galaxy distributions and peculiar velocities in regions currently hidden behind the galactic dust that blocks optical telescopes. The Zone of Avoidance, which has hidden the heart of the Great Attractor for decades, will become increasingly transparent as radio observations improve. The structure that has been felt more than seen for so long will finally come into sharp, detailed, unobstructed view. The ghost behind the wall will be photographed at last. The most massive gravitational structure in our cosmic neighborhood, the feature that defines our trajectory through the universe, will be mapped in its entirety for the first time. Perhaps the most striking aspect of the Great Attractor story is what it implies about the limits of what we can know. The Zone of Avoidance is a human problem caused by our position within the disk of the Milky Way. If we were positioned differently in our galaxy, or in a different kind of galaxy, the Great Attractor might have been discovered centuries earlier. Its hiding place is the result of our own cosmic address. We live inside the Milky Way's disk, which means we look through a thick lens of dust and gas whenever we gaze toward the galactic plane. The Great Attractor's discoverers had to infer its existence from its effects rather than observe it directly, in the same way that Neptune was inferred from the orbital perturbations of Uranus before it was ever observed through a telescope. In both cases, the invisible was revealed by what it moved rather than by what it appeared to be. Gravity spoke before light did. The universe communicated through motion, and the scientists listened carefully enough to hear it. Here, Neptune was predicted mathematically by the French mathematician Urbain Le Verrier, in 1845, based on the discrepancies in Uranus's orbit that could not be explained by the known planets. Le Verrier's calculation was so precise that when the German astronomer Johann Galle and his student Heinrich Louis de Rest pointed their telescope to the predicted position on the night of September 23, 1846, they found Neptune within 1 degree of where Le Verrier had said it would be. The Great Attractor was found by the same basic method 2 centuries later and on a vastly larger scale. Galaxies were the test particles, their velocities were the observational evidence, and the gravitational source was calculated from the pattern of their motions. The 7 samurai were the modern heirs of Le Verrier's method. They looked at a pattern of motion in the universe and said, there must be something there, something enormous, something hidden. They were right, and they had no telescope that could directly see it. They saw it with mathematics, with physics, with the logic of gravity applied at a scale Le Verrier I never imagined. The Great Attractor occupies a peculiar position in the hierarchy of things that are trying to pull the Milky Way in different directions simultaneously. On the smallest scales, individual stars are gravitationally influenced by their immediate neighbours. The Sun is gravitationally bound to the Milky Way, orbiting its centre every 225 million years at a speed of approximately 220 kilometers per second. The Milky Way is gravitationally bound to the Andromeda Galaxy in the local group and will merge with it in approximately 4.5 billion years. The local group is falling toward the Virgo cluster, and the Milky Way, carrying all of these local motions with it, is also falling toward the Great Attractor at 600 kilometers per second. All of these motions are superimposed. The solar system is simultaneously orbiting the galactic center, falling toward Virgo, and streaming toward the Great Attractor. You're not in one motion. You are in many, stacked on top of each other, all happening at once, all invisible to every sense you possess. The merger of the Milky Way and Andromeda, expected approximately 4.5 billion years from now, is itself a consequence of the gravitational dynamics that shape our cosmic neighborhood. The Andromeda Galaxy, also known as Messier 31, is currently approaching the Milky Way at approximately 110 kilometers per second, a peculiar velocity generated by the mutual gravitational attraction between the two largest members of the local group. When the merger occurs, the two galaxies will lose their separate identities. Their stars will be scattered into new orbits around a combined center of mass. The result, after a few billion years of gravitational settling, will be a new galaxy that astronomers have provisionally named Milky Way. Milky Way will then continue to fall toward the Great Attractor, carrying the merged mass of the Milky Way and Andromeda together, a slightly larger rounding error than before in the scale of Laniakea, continuing the same journey that has been underway for the entire history of the universe, toward a destination that will never be reached, on a trajectory set by the gravitational center of our supercluster before any of its stars existed. The CosmicFlows 4 dataset, published in 2022, contained nearly 60,000 galaxy peculiar velocity measurements and produced the most detailed map yet of the local cosmic flow field. The analysis of this dataset is ongoing. New techniques, including machine learning algorithms applied to galaxy morphology and spectroscopy, are being developed to increase the precision and efficiency of peculiar velocity measurements. The DESI survey, the Dark Energy Spectroscopic Instrument, mounted on the Mail telescope at Kitt Peak in Arizona, is measuring spectra for 40 million galaxies and quasars over its 5-year survey, providing an enormous new dataset for peculiar velocity measurements. The Euclid Space Telescope, launched by the European Space Agency in 2023, will provide complementary photometric data for over 1 billion galaxies. The flow field of the local universe is being measured with increasing precision by an entire generation of next-generation instruments, all trained on the problem of understanding where we are going, and what is pulling us there. The Great Attractor sits at the center of this scientific effort, the most important gravitational feature in our cosmic neighborhood. The Great Attractor's gravitational influence also has implications for the cosmic microwave background anisotropies that we observe today. The integrated Sachs-Wolf effect leaves subtle imprints on the largest scale temperature fluctuations visible in the cosmic microwave background map in the direction of large mass concentrations. Some researchers have suggested that the so-called low quadrupole anomaly in the Planck data, a measured deficiency in power at the largest angular scales compared to the predictions of the simplest inflation models, might be related to the existence of the Great Attractor or other nearby large-scale structures. This remains an area of active investigation, but the possibility that the largest anomaly in the cosmic microwave background might be linked to the gravitational feature that is actively moving us through space adds another layer of connection between the smallest and largest scales of cosmic physics. The universe is not a collection of independent phenomena. It is a single interconnected system, and the Great Attractor is one of its most prominent nodes, connected by physics and causation to everything from the quantum fluctuations of inflation to the temperature of radiation left over from the Big Bang. The velocity field maps produced by the CosmicFlows surveys reveal something fascinating about the geometry of Laniakea that is not immediately obvious from the descriptions of the Great Attractor as a single point. Laniakea is not spherically symmetric. It is elongated, stretched into a shape that extends further in some directions than others, determined by the asymmetric distribution of matter in the surrounding cosmic web. Matter has been accreting onto the Great Attractor region preferentially from certain directions along the filaments that connect it to the broader cosmic web. The result is a supercluster with a distinct three-dimensional morphology, a defined long axis, and a central convergence point. The Milky Way sits in the outer regions of this elongated structure, not at its geometric center, but displaced toward what was historically called the Virgo Supercluster region. Our position within Laniakea is eccentric in the literal geometric sense of the word. We are not at the center. We are somewhere toward the edge, looking inward toward a gravitational heart we can measure but never visit. The flow lines of Laniakea, visualized in the three-dimensional maps produced by the Tully team, resemble rivers flowing toward a drain. Every galaxy within the supercluster has a velocity directed toward the Great Attractor, and when those velocities are plotted as streamlines in 3 dimensions, they converge inward from all directions toward the same point, creating a pattern of unmistakable gravitational clarity. Traced backward in time, these flow lines show where the matter currently moving toward the Great Attractor came from. Traced forward, they show where it is going. The Milky Way's flow line points toward the Great Attractor, and following it forward in time requires the assumption that dark energy remains constant and that no unexpected perturbation alters our course. Under these assumptions, the Milky Way will continue its present infall trajectory for billions of years, making no measurable progress against the expanding universe, maintaining roughly its current position within Laniakea, while the structure around it slowly dissolves as dark energy pulls its outlying members progressively beyond reach. One of the subtle complications in mapping peculiar velocities is a phenomenon called the Fingers of God effect. In a galaxy survey, astronomers measure the redshift of each galaxy's light and use that redshift to infer the galaxy's distance and therefore its position in space. But peculiar velocities add to or subtract from the cosmological redshift, causing galaxies to appear displaced from their true positions along the line of sight. In a galaxy cluster, galaxies are moving in random directions relative to the cluster center, with velocities of hundreds of kilometers per second. These random motions cause the cluster to appear elongated along the line of sight in redshift space, stretching out into a finger pointing directly at the observer. This Fingers of God distortion must be corrected for when mapping the real three-dimensional distribution of matter. For the Great Attractor region, which contains one of the most massive galaxy clusters within several 100 million light-years, the Fingers of God effect is particularly pronounced and has historically complicated efforts to pin down the exact location and extent of the attractor. The density fluctuations that drove the formation of the Great Attractor were imprinted in the cosmic microwave background at the moment of recombination, approximately 380,000 years after the Big Bang. At that moment, before any stars had formed, before any galaxies existed, the pattern of slightly denser and slightly less dense regions was already set. Those patterns appear in the cosmic microwave background as temperature fluctuations of roughly 1 part in 100,000. The acoustic oscillations that drove those fluctuations, pressure waves in the hot plasma of the early universe, left a characteristic scale of approximately 500 million light-years imprinted on the distribution of matter. This scale, called the Baryon Acoustic Oscillation Scale, can be measured in the distribution of galaxies today and used as a cosmic ruler to measure distances across the universe. The Great Attractor region, with its scale of hundreds of millions of light-years, sits within the domain where the Baryon Acoustic Oscillation Scale is relevant, making it a structure whose formation is directly traceable to the physics of the first few 100,000 years of cosmic history. The Shapley concentration, sitting behind the Great Attractor at 650 million light-years, is the single most massive structure in our immediate cosmic neighbour auras. Its existence was noted by Harlow Shapley in 1930 when he observed an unusual concentration of galaxies in the constellation Centaurus. But the full extent and significance of the Shapley concentration was not appreciated until galaxy redshift surveys in the 1980s and 1990s revealed its true depth and richness. The Shapley concentration contains approximately 30 major galaxy clusters, including the rich clusters AY-Bell 3558, AY-Bell 3562, and AY-Bell 357162, and a Y-Bell 3571, connected by filaments of galaxies into a coherent supercluster complex. Its total mass exceeds 10 to the 16th solar masses, making it comparable to and possibly exceeding the mass of the Great Attractor region itself. The gravitational pull of the Shapley concentration is felt throughout Laniakea. It adds to the streaming velocities measured toward the Great Attractor direction, and disentangling its contribution from the Great Attractor's own pull has been one of the central challenges of peculiar velocity cosmology for more than 3 decades. Beyond the Shapley concentration, at even greater distances, lie further mass concentrations that may also be contributing to the Milky Way's peculiar velocity. The Vela Supercluster, identified in 2017 by a team led by René Kraan-Korteweg at the University of Cape Town, published in the monthly notices of the Royal Astronomical Society, sits approximately 800 million light-years away, also largely hidden behind the Zone of Avoidance. The Vela Supercluster is comparable in mass to the Shapley concentration and may be contributing hundreds of kilometers per second to our peculiar velocity. Its discovery was made possible only by new infrared and radio surveys capable of penetrating the Zone of Avoidance, and it suggests that the cosmic architecture beyond our immediate neighbourhood may be far richer and more complex than existing maps suggest. Every new survey that penetrates the Zone of Avoidance reveals new structures that were hiding behind our own galaxy's disk, each one adding another layer of gravitational influence to the complex velocity field in which the Milky Way moves. The total peculiar velocity of the Milky Way, measured against the cosmic microwave background rest frame at approximately 630 kilometers per second, is thought to be explained by contributions from at least 4 distinct sources: the Great Attractor region, the Shapley concentration, the Vela Supercluster, and the repulsion of the local void. The relative contributions of these 4 sources are still debated. Published analyses disagree on how much each structure contributes. The difficulty is that all 4 lie in roughly the same general direction of the sky, making it mathematically challenging to separate their individual gravitational effects. What is not debated is the total. The total peculiar velocity is real and large. It represents an enormous kinetic energy, the energy of the Milky Way's motion through the cosmic web, ultimately derived from the gravitational potential energy of the mass concentrations we are falling toward. The universe is not static, the Milky Way is not stationary, and the combined gravitational pull of 4 overlapping structures in the same direction makes our peculiar velocity among the largest of any galaxy in the nearby cosmic flow field. Pull back now and consider what this means for the human experience of existence. You are a living entity on the surface of a planet, inside a star system, inside a galaxy, inside a supercluster, all of it moving. The planet moves around the star moves around the galaxy moves within the local group falls toward the Virgo cluster, and everything falls toward the Great Attractor at 600 kilometers per second. You are a passenger on a vehicle you cannot see, inside a vehicle you cannot see, inside another vehicle you cannot see, each one larger than the last, each one moving without any sensation you can detect. The universe has given you no speedometer, no altimeter, no compass that points toward the Great Attractor. You live your entire life from birth to death as a creature in violent cosmic motion who experiences only stillness. The motion is real, the stillness is an illusion, and both are happening simultaneously, in the same body, in the same moment, in the same life that you are living right now. The idea that we are in motion, that the Earth is not stationary, has been psychologically difficult for human beings at every stage of discovery. The heliocentric revolution placed the Earth in motion around the Sun, a fact that took generations to become culturally accepted. The discovery of stellar motion in the 19th century showed that even the Sun is in motion, orbiting the galactic center. The discovery of the Great Attractor adds the most recent layer to this sequence of revelations, each one stripping away another illusion of rest. We are not at the center. We are not stationary. We are not even stationary relative to the galaxy or the local cosmic web. We are carried through the universe at speeds that make any human-made technology look placid by comparison. The fastest spacecraft humans have ever launched, the New Horizons probe, travels at approximately 14 kilometers per second. Our peculiar velocity toward the Great Attractor is 600 kilometers per second. We are 43 times faster than our fastest machine, and we have no engine and no fuel and no awareness whatsoever of the motion. The human scale of 600 kilometers per second becomes visceral only when you translate it into a number of human lifetimes. The average human lifespan's approximately 72 years, or roughly 2.3 billion seconds. At 600 kilometers per second over a full human lifetime, you travel approximately 1.4 trillion kilometers. That is about 148 light years. In an entire human lifetime, without going anywhere, without any spacecraft, without any effort, you travel 148 light years simply by existing on this planet. The nearest star to our Sun, Proxima Centauri, is 4.2 light years away. You cover the equivalent distance to Proxima Centauri roughly 35 times over in a single human lifetime. You cover the distance to the nearest star cluster, the Pleiades, at 440 light years, about a third of a lifetime. None of this travel requires a ticket or a seat or a decision of any kind. It happens to you by virtue of being matter in a universe with a Great Attractor. You are always already on the journey. The ethical and psychological dimensions of the Great Attractor discovery have been almost entirely absent from public discussion, and that absence is worth noting. The discovery that we are part of a supercluster, that our cosmic home has a gravitational center, that the structures of the universe are vastly larger than our species had imagined. These discoveries fundamentally reposition humanity within the cosmos. They do not diminish us in any simple sense. They contextualize us. They reveal that the universe has a geography, a texture, a three-dimensional landscape of mass and void that we are embedded in and moving through. We are not adrift in featureless space. We are on a trajectory within a structured cosmos, moving toward a destination we can identify and name and measure. The Great Attractor is our compass point. It is the direction in which the universe has decided to send us. The fact that we cannot perceive it directly, cannot feel the pull, cannot see the destination, does not make it any less real, and does not diminish the extraordinary achievement of the scientists who found it anyway. The relationship between the Great Attractor and the search for life beyond Earth is subtle but real. The distribution of mass in the universe determines the distribution of stars, which determines the distribution of planets, which determines the distribution of environments capable of supporting life. If the Great Attractor region is significantly overdense in matter compared to the cosmic average, it will contain proportionally more galaxies, more stars, more planetary systems, more potential habitats for life than an average region of the cosmos. Conversely, the voids adjacent to the Great Attractor region are correspondingly underdense, with fewer galaxies and fewer potential habitats for life. The distribution of life in the universe, if life exists beyond Earth, is therefore not uniform. Life is more likely to exist in the dense nodes of the cosmic web and less likely to exist in the voids. If there is intelligence elsewhere in Laniakea, it is statistically more likely to be concentrated toward the Great Attractor region than scattered uniformly across the supercluster. The Great Attractor may not just be pulling matter toward it, it may be concentrating the conditions for consciousness itself. The speed of our motion toward the Great Attractor raises a question about whether civilizations on planets in other parts of the supercluster would measure the same speed. The answer is that all galaxies within Laniakea have peculiar velocities directed toward the Great Attractor. Our 600 kilometers per second is the Milky Way's specific velocity, determined by our location within the flow field. Galaxies closer to the Great Attractor move faster, having fallen further down the gravitational slope. Galaxies further out move slower. Galaxies in directions perpendicular to the pull of the Great Attractor have smaller components of velocity directed toward it. If intelligent civilizations exist in galaxies throughout Laniakea, each of them would measure a peculiar velocity directed toward the Great Attractor, each with a different number, determined by their distance from the center and their history within the flow field. Our 600 kilometers per second is not a special or unusual value. It is simply our particular address on the gravitational map of Laniakea. Every galaxy in the supercluster has its own address, its own speed, its own infold trajectory toward the same unreachable center. The Great Attractor offers an extraordinary demonstration of the reach of gravity across distance. Gravity is the weakest of the four fundamental forces of nature. The electromagnetic force is 37 orders of magnitude stronger. The strong nuclear force is stronger still. By every measure of force strength, gravity is catastrophically weak. And yet gravity is the force that shapes the universe on the largest scales, because it is the only force that is always attractive and that has infinite range. It never cancels out. Every positive electric charge is paired in the universe on large scales with a negative charge. But there are no negative masses. Everything has positive mass and everything attracts everything else. Across hundreds of millions of light years, the cumulative gravity of an overdense region can set an entire supercluster in motion. The Great Attractor is the universe's most eloquent demonstration of what the weakest force in nature can accomplish when it is given enough mass and enough time. It wins not because it is powerful, but because it is patient and ubiquitous and never stops. The motion of the Milky Way toward the Great Attractor is part of a larger pattern of motion that becomes visible only when you map the velocity fields of thousands of galaxies simultaneously. The pattern reveals what cosmologists call the cosmic flow field, the three-dimensional distribution of velocities generated by the gravitational landscape of the nearby universe. In the cosmic flow field, the Great Attractor appears as the dominant attractor, gravitational sink toward which all surrounding matter flows. But the flow field also reveals something else. The Great Attractor is not the only attractor in our neighborhood. The Shapley concentration behind it is another. The Perseus-Pisces supercluster, located in the opposite direction from the Great Attractor at roughly 220 million light-years, is a third. The cosmic flow field is a complex three-dimensional landscape of competing gravitational influences, with the Great Attractor region as the dominant feature but not the only one. The Milky Way moves through this landscape in a direction determined by the vector sum of all these forces, with the Great Attractor winning the tug-of-war by the margin of our 600 km per second infall. The resolution of the Great Attractor's true identity, not just the Norma Cluster but the extended Laniakea Supercluster, required a shift in how astronomers defined cosmic structures. Traditional methods relied on galaxy density, on counting how many galaxies per unit volume existed in a given region. By these density-based methods, the Great Attractor region was always going to be hard to define precisely, because its mass is distributed over an enormous volume at only moderate overdensities for most of the volume. The Tully team's innovation in 2014 was to define cosmic structures not by density but by dynamics, by the pattern of how matter flows. Define the boundary of Laniakea as the surface where the flow direction changes, where matter transitions from falling toward the Great Attractor to falling somewhere else, and suddenly the supercluster has a precise, physically meaningful definition. It is the gravitational watershed. It is the drainage basin of the cosmic web. And everything on this side of the divide, including the Milky Way, belongs to it. The definition was elegant and the implication was staggering. Our supercluster was vastly larger than anyone had previously measured. The drama of the Great Attractor story is also a story about scientific methodology, about how knowledge is constructed when direct observation is impossible. The Zone of Avoidance made direct observation impossible for decades. What the Seven Samurai had instead was indirect evidence. The motions of hundreds of galaxies spread across the sky, each motion a data point in a vast statistical argument. From these data points they inferred the existence, location, and approximate mass of something they could not see. This is one of the most powerful and purest examples of scientific inference in modern astronomy. The discovery of the Great Attractor is not a story of someone looking through a telescope and seeing something unexpected. It is a story of someone measuring velocities, running calculations, and deducing that reality must contain something the data demands. The universe does not always show us its face. Sometimes it only reveals its effects, and the scientist's job is to reconstruct the cause from those effects with enough precision and enough data that the conclusion becomes inescapable. The Seven Samurai made that conclusion inescapable. The discovery of the Great Attractor illustrates how scientific understanding is built incrementally, each generation of astronomers adding to and sometimes correcting the work of the previous one. The Seven Samurai identified the streaming motion in 1987. Subsequent surveys in the 1990s located the Norma Cluster as the visible core. The 2000s brought better infrared and radio surveys that partially penetrated the Zone of Avoidance. The 2010s brought the CosmicFlows surveys and the formal definition of Laniakea. The 2020s are bringing the next generation of surveys that will refine the picture further. Each step corrected misunderstandings from previous steps. The Great Attractor was initially conceived as a more localized object than it turned out to be. Laniakea was larger and more complex than the Virgo supercluster it replaced in our address. Science does not arrive at final answers, it refines its approximations, each generation seeing further than the last, each revision bringing a little more of the truth into focus without ever claiming to have seen it all. The story of the Great Attractor is still being written, and the next chapter will be written by the surveys now coming online. There is something deeply human about the project of mapping where we are in the universe. Every civilization that has looked up at the night sky has tried to locate itself, to understand its position relative to the stars and the cosmos beyond them. The ancient Greeks placed Earth at the center of the cosmos. Copernicus moved the sun to the center. Shapley and Curtis debated whether the Milky Way was the entire universe or just one galaxy among billions. Hubble resolved that debate in 1924 by measuring the distance to the Andromeda Nebula and showing it was far too distant to be part of our galaxy. Each answer to the question of where we are has been replaced by a larger, more humbling answer. The Great Attractor and Laniakea are the current best answer. They will not be the last. Future generations will likely discover structures beyond what we can currently map, larger basins of attraction, more distant over densities, deeper layers of the cosmic hierarchy. The question of where we are in the universe will keep demanding better answers, and the universe will keep providing them. The speed of 600 kilometers per second toward the Great Attractor sits in a peculiar relationship with other cosmic speeds that are worth comparing. The expansion velocity of the observable universe at its outermost edges, due to dark energy, exceeds several times the speed of light. The most energetic cosmic rays ever detected carry energies equivalent to particles moving at nearly the full speed of light. The jets produced by supermassive black holes in active galactic nuclei can reach velocities approaching 50% of the speed of light. Against these extremes, 600 kilometers per second is a gentle, almost placid speed. It is 1/500th of the speed of light. It is fast by every human standard and slow by every astronomical one. And it is the speed at which you, specifically, are being carried through the cosmos by the largest gravitational structure in your neighborhood. Fast enough to cross the United States in 9 seconds. Slow enough that you will never, ever reach your destination. The universe arranged things this way precisely. There was never any possibility of arrival. Gather everything you have heard in the past hour and hold it in your mind for a moment. The Great Attractor is real. Its pull is real. The 600 kilometers per second is real. The Laniakea Supercluster, 520 million light-years across, containing 100,000 galaxies, is real. The Shapley concentration behind it and the Vela Supercluster beyond that are real. The Zone of Avoidance that hid all of this for so long is real. And the accelerating expansion of the universe that makes the Great Attractor permanently unreachable is also real. All of these things are simultaneously unambiguously true, and the question that demands an answer is not an astronomical one. The question is what you do with this information. Because the universe has offered you something extremely rare. It has shown you through the painstaking work of thousands of scientists across decades the actual structure of the cosmos in which you are embedded. It has given you the address. It has described the motion, and it has named the destination that you will never reach, but toward which you will always be traveling. The fact that the destination is unreachable is not, in the final analysis, a tragedy. It is the architecture of the universe. Gravity-built Laniakea. Dark energy ensures that most of it will never collapse. We will never fall into the Great Attractor because the universe will not allow it. But we are falling toward it, and have been falling toward it for every moment of the Milky Way's existence, and will continue falling toward it for every moment of our galaxy's future. This sustained, permanent infall towards something that can never be reached is not futility. It is motion. It is trajectory. It is the universe's way of saying that the journey itself is the state of being, not the arrival. Every galaxy in Laniakea is in the same situation. Every galaxy is falling. None will arrive. All are in motion. The Great Attractor defines the direction. The universe defines the terms, and the terms are, in the most literal sense, universal. Every conscious being in every galaxy in our supercluster, if any exist, is on the same endless infall. The motion is shared. The destination is shared. The impossibility of arrival is shared. The reframing that the Great Attractor requires is fundamentally about scale. Human life occurs at a scale so many orders of magnitude smaller than the structures we have been discussing that the usual emotional tools, fear, urgency, the sense of personal danger, are essentially useless here. The Great Attractor is not a threat. It is not approaching. It is not doing anything to you that it was not doing to the first organisms that ever lived on Earth, and to the planet itself before life existed, and to the solar nebula before the planet formed. The pull has been constant. The speed has been roughly constant. Everything you love, everything you fear, every moment of triumph and disaster in human history, all of it has occurred at this velocity in this direction, without interruption, without variation, without any notice from the universe that any of it was happening. The Great Attractor is indifferent to human concerns in the most complete way possible, and there is something strangely comforting in that indifference. It asks nothing of you. It does not require you to understand it. It pulls you regardless. There is a specific kind of comfort that comes from understanding very large things. Not the comfort of safety, because large things are not usually safe, but the comforts of context. When you know that you are a small part of a very large system, when you understand the scale of the forces that shaped you, and that continue to move you through the cosmos, the small concerns of daily life take on a different quality. Not smaller or less important, but differently situated. You can hold two things at once: the absolute reality of what matters to you personally, and the absolute reality of a universe that operates on scales and timescales that make those personal concerns invisible to any external observer. The Great Attractor does not diminish your life. It situates it. It gives it a cosmic address. You are here in Laniakea, falling toward the Great Attractor, on a planet orbiting a star, living a life that is genuinely important in the only frame of reference that has ever mattered to any conscious being, which is your own. The 7 samurai who discovered the Great Attractor in 1987 were not looking for something this large. They set out to map the mass concentrations in the local universe and found, instead, a structure that forced a complete revision of how cosmologists thought about the largest scales of cosmic architecture. Alan Dressler, Sandra Faber and their 5 colleagues did not know, when they began their survey of galaxy velocities, that they were about to discover the gravitational heart of a structure containing 100,000 galaxies. They were just doing the work. They were measuring distances, calculating velocities, running analyses, writing papers. The discovery found them, not the other way around. This is how most of the most important discoveries in science happen. Not by seeking something specific and finding it, but by looking carefully at what is actually there and following the evidence to wherever it leads. The Great Attractor was hiding in plain sight, encoded in the motions of hundreds of galaxies, waiting for someone methodical enough to notice the pattern and rigorous enough to trust it when they did. The cosmic web of which the Great Attractor is a node is itself a structure of astonishing complexity when visualized through detailed computational models. The Illustris simulation, the Eagle simulation, and the Millennium simulation are among the most detailed computational models of cosmic structure formation ever run. In these simulations, the universe begins smooth and nearly homogeneous, with only tiny quantum fluctuations seeding the subsequent growth. Over billions of simulated years, the structures emerge, sheets and filaments forming as matter collapses along preferred directions, voids growing where matter has been drained away, clusters forming at the intersections of filaments, and superclusters like Laniakea taking shape as the dominant nodes of the cosmic web. The simulations match observations so well that cosmologists use them to test theoretical predictions against the real universe. And in every simulation, structures like the Great Attractor emerge naturally, inevitably from the physics of gravity acting on small initial fluctuations. They were always going to be there. The Great Attractor was not a surprise to the equations. It was a prediction they'd been making all along. The question of whether the Great Attractor is typical or exceptional among the structures in the observable universe has a nuanced answer. In terms of mass per unit volume, the Great Attractor region is overdense but not extraordinarily so by cosmic standards. There are other superclusters in the observable universe that are comparable in mass. There are larger structures. The Sloan Great Wall, a filamentary structure over 1 billion light-years long detected in the Sloan Digital Sky Survey. The Hercules Corona Borealis Great Wall, a hypothetical structure stretching several billion light-years that, if confirmed, would be the largest known structure in the observable universe. What makes the Great Attractor exceptional is not its absolute mass, but its relationship to us. It is our attractor. It is the dominant gravitational influence in our supercluster. It is the feature that defines where we are and where we are going. In the catalogue of structures in the observable universe, there are thousands of great attractors, each one the gravitational centre of its own region. But this one is ours, and that fact alone makes it singular in the only frame of reference we will ever inhabit. The deepest lesson of the Great Attractor may be this: the universe is not a collection of isolated objects floating in empty space. It is a dynamic, interconnected system of matter in motion, organised by gravity on every scale from atoms to superclusters, with each scale embedded within the next in a hierarchy of structures that extends from the quantum to the cosmic. You are embedded in this hierarchy. You are not a spectator. You are a participant. The matter in your body was forged in stars. Those stars formed in the Milky Way. The Milky Way formed within the gravitational influence of the local group and Laniakea. The Great Attractor shaped the environment in which your galaxy formed and evolved. And the quantum fluctuations that seeded the Great Attractor occurred in the first instance of the universe that created everything. You are in a chain of physical causation that spans the entire history of the cosmos, a product of the Great Attractor, not its victim, its result. And the result is alive and aware and capable of understanding the cause. That fact is extraordinary. It is a strange thing to know the name of the force that is moving you. Most people will live their entire lives without thinking about the Great Attractor, without knowing that they are falling toward it at 600 kilometers per second, without understanding that the direction of their cosmic journey has been set since before the Earth existed. And perhaps that is the right way to live most of the time. The practical demands of existence are not served by constant contemplation of supercluster dynamics. The present moment has its own gravity, but occasionally, in the quietest hours of the night, when the noise of ordinary life falls away and the mind turns toward larger questions, it is worth remembering that you know something remarkable. You know where you are. You know where you are going. You know the name of the thing pulling you there. Very few species in the history of Earth have ever known any of those things, and the knowing all by itself is a kind of navigation. You are not lost. You are in Laniakea, and you are falling toward the Great Attractor, precisely where the universe put you. The night sky above you containing the direction of Centaurus, the invisible centre of your supercluster. You cannot see it with the naked eye. You cannot see it with most telescopes. The galaxies that mark its position are hidden behind the dust of the Milky Way, inaccessible to optical light, speaking only in radio and infrared and X-ray wavelengths. But it is there, and it is pulling everything in your cosmic neighborhood, including every star you can see tonight, including every galaxy in the Milky Way, including the Sun, including this planet, in the direction of something vast and hidden and patient. The universe operates on timescales that make human history a barely perceptible flicker. The Great Attractor has been pulling the Milky Way toward it for billions of years, and will continue doing so for billions more. The journey is older than the Earth. It will outlast everything built on its surface. Tonight, the pull continues, 600 kilometers per second, steady, silent, unstoppable, and you are on the journey whether you choose to think about it or not. There is comfort in the permanence of this motion. The Great Attractor does not change its mind. It does not have moods or doubts or second thoughts. It exerts the same gravitational pull today that it exerted when the first multicellular organisms appeared in the oceans of the early Earth. It will exert the same pull when the Sun grows into a red giant and engulfs the inner planets. It will exert the same pull when the Milky Way and Andromeda merge into Milcom Ada, billions of years from now. The Great Attractor is the most reliable force in our cosmic neighborhood, not because gravity is special in any mystical sense, but because the laws of physics are consistent. The same equations that describe the fall of an apple describe the fall of a galaxy. The universe applies its rules everywhere, without exception, without prejudice, without pause. We are not special in our motion. We are consistent with the physics. The physics has been consistent since the first moments of the universe. And in that consistency there is something that functions in the quietest and most accurate sense of the word, like peace. So take a breath. Let yourself be still for a moment, because stillness is what the body knows even when the cosmos knows something different. You're moving at 600 kilometers per second toward a structure 250 million light years away. You will never arrive, neither will anyone else. The Great Attractor will always be ahead, and the expanding universe will always keep it there, just beyond reach. Always pulling, never waiting. And perhaps that is enough to know that the universe has a direction, to know that we are part of a structure with a name, to know that the mathematics of falling through space in the direction of something enormous and hidden and incomprehensible to the human eye is the same mathematics that holds water in a glass and keeps the moon in its orbit and makes the tides come in on schedule every single night. Gravity is gentle at this scale. It carries you without harm. It asks nothing in return. The Great Attractor pulls you towards sleep, slow and steady, and the universe moves on.